Hi fellow hams, welcome to the shack and welcome to school holiday time. It is pouring rain outside, which is wonderful because it means I can stay inside and do lots of ham radio stuff and maybe create some calmness in the chaos that is my shack presently. In today's video, we are doing a 100 watt RF tap, a very simple 100 watt RF tap. And I make lots of discoveries along the way, one of which saves the day because I nearly smoked my Tiny SA had I plugged it in with the understanding that I did have. So watch the video and you will learn a lot along the way, as I did. But if you want to fast forward to the end where you see this chalkboard scene, I will describe the circuit, tell you the values that I've used, and you can have a go at building the circuit. Like I always say, once you build the circuit, check it on your Nano VNA, make sure that it's giving you the attenuation that you require. I do my best to make sure this is all correct, but I do make mistakes, as you all know. So by all means, build the circuit, but have a go at checking it as well. And if you want to comment below about the circuit or things that you can see that might be wrong, by all means, also do that. We all learn together by doing this. Roll the promo. Well, hi there folks. It is finally school holiday time. Finally there is time to play ham. I've got lots of plans, hopefully enough energy to do it. As you can see here, we have my tiny spectrum analyzer, the Tiny SA, and my Chinese HF amplifier, which has been featured in quite a few videos. The plan is to take this now and test it for spectral purity to make sure that it's not splattering all over the bands. Now we did install a low pass filter and that should have mitigated most of the issues, but we really should check it if we can. So I'm going to plug this 50 watts into my Tiny SA and just see what happens. On second thoughts, I might just dial the power back a bit. So we're going to have to find some way of taking the 50 watts that's coming out of here and making it so teensy tiny that our teensy tiny spectrum analyzer can cope with it. You know, I do like to let the smoke out of things, but I do like having this piece of test equipment around, so we're going to have to look after it. We're going to have to come up with a solution for this dilemma. If we're going to test our amplifier for spurious emissions to make sure that it's clean, we're going to need to dial back the power, and the technical way of saying that is to attenuate. We need to make it weaker so that it's not going to damage the piece of test equipment. Now, in a previous video, which I'll link to below, I wanted to test my Baofeng, which I had quite a while ago, and I did want to check it to see how clean it was. So I went and bought an attenuator online. Now that is an attenuator that will take up to 10 watts, and it says on the front of it basically DC to daylight, DC to 3 gigs, and that was all well and good, but unfortunately while I was testing to see whether the Baofeng was clean, and it actually appeared to be a reasonable output, it decided to die on me. So after outlaying for this, and it wasn't hideously expensive, but certainly wasn't the cheapest thing to buy online. Now I imagine were I to want to get a 100 watt unit, I'd probably be looking at 60 to 80 bucks. And if I needed to spend that money, I would. But for HF purposes, there is a way cheaper and a way simpler option, provided you've got your dummy load on hand for HF. It will get you out of trouble and get you an accurate enough measurement and provide the attenuation that you need. Now the device I'm talking about is called an RF tap, and with a handful of connectors, a few resistors and a capacitor, it's done. So it's very, very cheap to construct. And as you all know, I like to give credit where credit is due. And I got the idea for this and a lot of the information from another ham by the name of Stuart Sheldon, Alpha Golf 6 Alpha Golf. and he showed me how to build this, and also some of the sources of information that he also went to. I would say with anything that I'm telling you about, anything you do so at your own risk. I am not an expert. As you will know, I am a bona fide clown. So folks, with no further ado, let's get on with the build and let's get on with the testing. Okay, welcome back to the test bench. This is the basic circuit for our RF Tap Attenuator, and like I was saying, we're looking at approximately minus 40 dBm, or thereabouts. And if you were to attach this to an input on your spectrum analyzer that's 50 ohms as well, we're actually changing this impedance and what's happening here. And I've been told it changes it down to about minus 39 dBm or something. So for all intensive purposes, this is a minus 40 dBm attenuator. It's just a very, very basic voltage divider with 50 ohms here and on R2, which is going to be just a couple of paralleled resistors. In my case, I think I've gone 4 because I didn't have 2-watt resistors. I only had 1-watt resistors, so I've done 4 of those in parallel rather than 2 to get myself up to the wattage. Now, from my understanding also, when the calculations were done for this circuit, you're looking at about 2 watts or so of dissipation, slightly over 2 watts. So you want to have over 2 watts for your resistor values. I think I've more than compensated for that situation, but he had 3 820 ohm resistors in series that were 2 watts to bring himself up to 2460, and a parallel pair of 100s to get to 50. I'm going to do a little bit more convoluted arrangement because I couldn't find the values I needed, and I'm hoping I get close enough to 2460. I may have to muck around with that a little bit, but we'll start putting resistor values together, and we'll see if we can get to a approximate 2460. Enough blabbering on. Let's get on with the build. Oh, and by the way, C1 is there just to remove any DC offset, because a lot of these devices don't like to see DC, so it's just to make sure that there isn't any DC there. It's going to be a virtual dead short for RF. 0.1 microfarads does not need to be a high value. Apparently the voltages here are quite low. He's using a 50 volts working capacitor. I'll use what I've got to hand, and we shall go from there. Let's go. Well, I am hoping I can finish this before World War III starts. I've got to stop watching the news. These are the resistors. Look, I just grabbed what I could find. Failed on Ohm's law on Friday afternoon, big time. These are 1K. I think they're 1 watters. And we've just thrown lots of resistor values together to get as close to 2460 as we can. I got to 2453. Good enough for me. And that is our 2 100 ohm resistors in parallel. I also went and looked at die-cast boxes, and they were hideously expensive, $17, $18 at JCar. This is a tin box that was originally cough lollies. And I'm going to give this a spray and probably earth the lid to the base and put the connectors in this. Give it a spray, make it nice and black. I could leave the beautiful decals on it, but I'm thinking I've got some black spray paint, so I'll give it a spray. And we will put our through here and our connector for the actual scope over here. And this should make a nice little attenuator to test our amplifier. Just so you know, I'm actually not lying. These are the resistors. Ohms value 2453. That's our 2 100 ohm resistors, which should give us a 50 ohm in parallel. .2. So that is that. We just need to get ourselves a capacitor, 0.1 microfarad, and we can start building this. Well, I'm also going to need to drill this as well, so I might go and do that now. So the case spray is complete. We can start installing our connectors now. I did lose one, so I had to go and buy another one. It fell off the table, and Lord only knows where it rolled to. But occupational hazard, working outside and not being careful. I'm now getting to the point where the shack is becoming so discombobulated that I am going to have to, at some point in time, commit a neatness. But at the moment, I'm too excited by upcoming projects. But yes, we will be trying to get things a little bit more organized. Let's get these connectors into the case, and then we shall proceed with the very, very simple act of wiring it all up.
That's on. Yeah. I'm also guilty of not doing a lot of the time, which has also got me in a lot of trouble, is once you're done, put it all away.
So that is the wiring so far. What I will do also is put a piece of braid between the bottom of the case and the top, just so that it's nicely earthed both bottom and top. And then we will do the attenuation test on it. Make sure it's behaving itself, make sure we don't have any silly little shorts or anything that's going to cause issues. And we will be ready to give it a crack. There we go, minus 40 dBm. And I could have through on here, but that's pretty damn obvious. Okay, calibration is done. And we have down at our 1 meg scale, minus 32. So it's not quite as much as we wanted. Coming up, fairly flat response. We'll get up to 15, which is halfway. So even at 15, we're only minus 33. So it's only a 1 dBm difference. And when we go all the way up to 30, it does tail off a little bit. Down at 30, we're at minus 40 dBm. So perfectly flat, no. But we're going from about minus 32 to minus 40 dBm. And that is fine enough by my standards, my very, very marginal standards. Oh, I did forget to mention, this is a 50 ohm dummy load, for those that were wondering what the money box is. It's a low power 50 watt dummy, but I will be setting up on my main operating bench because I will need to avail myself of my homebrew 100 watt Cantenna as a dummy load. And we will have a look and see what the amp's doing harmonic wise. Fingers crossed it's not filthy dirty. And really lucky we've checked. This is the safe measurement of the output of transmitters Tiny SA. And we can see here that for the required attenuation between transmitter and Tiny SA, you actually need, for a 100 watt transmitter, 60 to 70 dB. So my attenuator that I have constructed here, it says it's minus 40 dBm, but it's actually closer to high 30s. So what to do? Lucky I haven't just gone and plugged it straight in like I normally would. We have, like I said, this type of attenuator. It's 40 dBm, and it's a 10 watt attenuator, so obviously I can't use that directly out of the transmitter, but I can plug that into the tap to get me up to the required amount. So very, very lucky that I actually checked, because I would have smoked my spectrum analyzer, which would have been a very sad day for me. Now, I've kind of worked out why I was about to create a disaster for myself. This is the video from the gentleman that Stuart Sheldon, who's given a great account of how to build this tap. But he's using a spectrum analyzer that'll take 100 milliwatts. Okay, listen to this.
I want to get my signal on that attenuated output when before I hook it to a scope or a spectrum analyzer or something like that. And I use the basis that my spectrum analyzer does not want to see more than 100 milliwatts. It says you put more than 100 milliwatts in it and it's going to go pop.
Okay, so more than 100 milliwatts and it's going to go pop. Well, unfortunately, the Tiny SA, which is not the spectrum analyzer that Stuart has plus 6 dBm or a 5 volt DC maximum. So we've gotten rid of all our DC via that capacitor, so we don't need to worry about the DC happening at the input. But plus 6 dBm in milliwatts, for those that are math challenged like me, I've just done the Google search, is 3.9 milliwatts. So it's an order of magnitude that's way, way smaller. Hence the Tiny SA dictating that it wants a 70 dBm attenuation. So we could just go back to the drawing board and rebuild this attenuator, or we can just, like I said, grab our 40 dB attenuator, and that'll get us out of trouble quickly, and it'll get me testing as I require. So I'll be doing that. But were you to want to rebuild this tap, I will very, very quickly find out what value resistor you'd want to be looking at. But like I said, after you build your attenuator, test it on a nano VNA and make sure you're getting the attenuation required, because you don't want any nasty surprises. So the maths is in, and it looks like for a minus 70 dBm attenuation, if we're looking at having the resistance value of 50 ohms as our R2 value in that original circuit diagram, and we're looking at a 50 ohm impedance of the testing device, we're looking at about 79 kilo ohms. And obviously, if you're then going to a high impedance test device, the attenuation changes slightly, but with a 70 dBm for your Tiny Ultra, that should be fine up to 100 watts, according to my calculations. And here we have the test set up. Like I was saying, we have 40 dBm, which for Stuart's purposes was fine, because he had a test instrument that could take, I think it was 100 milliwatts on the input. Tiny SA does not like that, like we said. So we need at least 70 dBm for 100 watts. So at the moment we have our 40 dBm, but we've added this 10 watt 40 dB attenuator through attenuators. So 40 plus 40, we've got 80, slightly less than 80, because the measured attenuation was slightly less than 40. It was in the high 30s, but more than enough. We'll be over 70 dB attenuation, so that should be fine. So that's how we've got the attenuation set up, and I'll just swing around and show you that we've got our Tiny SA just over here. So we'll set that all up and we'll hit transmit, and you can have a look at what the spurs look like. Okay, folks, it is pouring rain, and I'm hoping the sound is usable on this video, but it's going to rain all weekend, so onwards and upwards. We needed to set all the different levels in here. I've gone into attenuate, and that's set to 0 at the moment. We have more than enough attenuation happening.
We also went into measure, and we selected harmonic, which is great. And we also needed to go to level and set our external gain. So external gain, I'll just reset it again. We go to minus 73. And that's because when we measured our times 1, when we measured our original RF Tap Attenuator, we had a 33, minus 33 dBm attenuation. We've now also got the 40 dB attenuator in, so 33 plus 40 is 73. And we are looking for all the harmonics must be below 50 dB. They must be 50 dB below the carrier. So we'll have a look. And initially when I was doing this, I was getting mostly 50s and 60s, but there was one value that was a little bit high. What I've done is I've just wound the drive back on the Hermes, and we'll have a look at what we're getting now. And you can see here now, when they settle down, they are all above 50 difference in value. So yes, there is a lot of harmonics, but none of them are over the amount that they should be. So I will just freeze that just to make sure that you believe me. So if we go trace, we can hit freeze when things settle down. So you can see there on this screen, I might just try and zoom in. That we have our difference from the carrier on our second harmonic, 54, and then we've got 53, 51, 50.7, 62. So all of those values are greater than 50 dB compared to carrier. So they sneak across the line. And obviously it'll be different for different filters, but thus far the transmitter is clean.
Okay, for the folks that watched the entire video, you will know that my attenuation was of the order of about minus 33 dB, down to about 40 as you went from 1 to 30 megs. Reasonably flat, not perfect. This is by no means a perfect way of getting attenuation, but it's certainly a cheap way of getting it. It gets you out of trouble. Now, it's basically a simple resistor divider. So you've got an R1 and an R2 value. For the minus 70 dBm that I required for my Tiny SA, I would need an 80K and a 50 ohm. Now, as you all know, I ended up on the output of mine putting a minus 40 dB attenuator that I did have because I stuffed up on the amount of dB attenuation that I did need. Because the video I was watching, the gentleman that was building the circuit had a spectrum analyzer that would take up to 100 milliwatts, and the Tiny SA can take way less than that. It's down in the single digits of milliwatts. So that is why they recommend 60 minus 60 to 70 dBm. So we need a good amount of attenuation for the Tiny SA. This circuit here, B and C connector, we go straight through. We have earths happening here. Now all of these resistors here, 233K in parallel, 233K in parallel, 47Ks in parallel, and 47Ks in parallel, all joined together, create an 80 kilo ohm resistor. So you need 80 kilo ohms. Do it any way you like. I do know that you do also need to understand there's a certain amount of dissipation that needs to happen in the circuit, which we'll talk about shortly. This is a 100 ohm pair in parallel, which gives us the 50 ohms we require to earth. And this capacitor here, it's a 0.1 microfarad.
I'll just write that on there. Okay, formulas. The drop in dBm is equal to 20 log R1 on R2. So if you look at this simplified circuit over here, R1 is the top value, which is the 80K if we want to get minus 70 dBm, and R2 is the 50 ohm resistor. So if you put these values into the formula, 20 log 80,000 over 50, you should get a value of 70. Check it if you don't believe me. Now we also have a voltage formula here. So you put your value of watts that you're going to be using through the tap. In this case, it was 100 times 50. And then when we get that voltage value, we swap it into this formula here. Watts is equal to V squared divided by R1, which is our 80K value in this case. And what that gives us is a 0.062 watts, a very small amount of wattage. So all of these resistors here, for dissipation purposes, are really not required. You get away with 1 watt resistors if you could get an 80K and a 50 ohm. Standard component values, I have not got a clue. I would have to, go and do some research for that. So I just cobbled together what I had. Having said that, you could actually work out what your power dissipation is at, say, 500 or 600 watts. And if the attenuation was enough, you could use it at a higher wattage. So by using higher value resistors, you can probably use it at a higher wattage. Now, these are 1 ohm resistors that I would use, or that I've actually purchased. I haven't actually put them into the attenuator yet. So this is a proof of concept, but I am certain that it will be okay. So if you do build this attenuator, like I said, check it and let me know how it goes, because I'd be really interested to do it. Now, I'm certainly going to renovate my attenuator when I get a chance, but there's just so much stuff at the moment that I need to get done. Now, the checks on the amplifier, they all turned out pretty good. All over 50 dB on the spurs that I could see, and I am happy with how that looks. And that means that I can continue on with rolling my own low-pass filters and getting it all in a box. And that means my Hermes light will do 40 to 50 watts, which for me, as most of my operation is QRP, is more than enough power to play around with. I also have a FT101E that I want to start renovating, and so many other projects. So all of that's going to be happening over this break, hopefully, if things do not conspire against me. 73, and I shall see you in the next episode of The Art of Engineering.